Hey, hello everybody. Welcome back to the stream. Before we get started, are there any questions about things we did in the previous two parts? So the current status of the compiler is that we are able to parse simple expressions, only consisting of integer literals at the moment. So for example, like 11. This of course doesn't do anything. So we also added the ability to print things by adding an extension, a print statement. And we are able to assert that two values are equal with another extension. So this is then translated into the AST, and where everything is like a function body has a block statement as its child, which has expression statement as children, or built-in statements, and we then translate that into bytecode. So I've hacked the local copy of lauf to modify to disable constant folding, so we can actually see the things going on. So every expression pushes its value onto the stack. So the 11 here is pushed onto the stack, and then an expression statement simply discards it. So we pop that again. When we want to print something, we evaluate the expression, which pushes it onto the stack, and then we call the print built-in, which leaves the value on the stack, so we also pop it. And then the assertion is a binary expression, so we put each operand, both are 11, OX11 in hexadecimal. Then we call our equal function, we call assert, and then we're done. And finally, we have this implicit return 0 here at the end. So we push 0, and then we return. So let's just pick up where we left off last time, which were we added binary expressions. So currently we only have equality. Let's just implement the other one as well. So we've got equal, not equal, less than, less equal, greater than, and greater equal. The remaining comparison operators. This means that we need to add them to the, first of all, we need to be able to print them. So let's print them as well. Do not, okay. So not equal, less than, less equal, greater than, and greater equal. This should compile now. Take care of that later. Let's add them to the parser next. So we are parsing expressions here using Lexi's expression production, which is like a built-in way of doing operator precedence parsing. We're currently only having equality. If we look at the official grammar here in the C standard, expressions. We can see here that we have equality expressions. They use either like equals equals or not equals, and their operands are relational expressions. So less than, for example, binds tighter than equals equals. They have a higher precedence. I never know which way the numbers go. But they bind tighter. And because we can see here that equality expression is the operand on the left, this means that we have A equals equals B equals equals C. We will first like the left, it's left associative. So this is what we've written here. So equality is an infix left associative operator, and we have equals equals, or we can have not equals at this level. So not equals that operator. And then the operand is a relational expression, which is the other comparison. So the operand is relation, equality relational. So equality relational. This is also left associative. And the operators here are the less, less than, less equal, greater than, and greater equal. And the operand, the proper operand for a relational expression is a shift expression. We don't have those yet, so we immediately jump to atom instead. And here the operand is a relational expression. We don't need to change anything in the callback, because when we pass a binary expression, we populate the binary expression opt here. This will always have the correct value. So this will create the correct tree. And finally, we need to adjust cogen. So the way cogen works is that each sub-expression pushes its value onto the stack. And because we visit the binary expression has as its children, you don't. So what I think I need to use this operator here instead. Okay, and so a binary expression has as two children, which are the left and the right node, which means that when we traverse the tree, after we visited, so traversal will visit a binary expression node, it will then visit its left child, then its right child, and then go back to the binary expression node. And when we visit it the second time, we know that the values are pushed onto the stack. So as we can see here, at this point we've visited it the second time and we've pushed it to a point onto the stack. So this is specified with the callback here. We want to visit it on exit, because we know at this point the operand has been pushed onto the stack. And then we want to do the comparison. In this case, we're calling our built-in function that compares to its. The reason we needed to write a built-in function to compare to ints was because Lexi only has a built-in to do a three-way comparison. Allow with int. So this will push. So this will result in -1, 0, or 1, depending on the result. And we want a 0 or 1 if it's equal. And there was no way to convert that. I've since added an instruction to convert it. So cc for condition code and equal. So this will do a three-way comparison, which result in -1 or +1. And if it's 0, then we then turn that into the equality result. And this means implementing the rest is very straightforward. So if we want not equal, we want not equal. Less than means we want less than. Less equal, greater than, greater equal. Now we don't need this built-in anymore. So this works the same. So now we are calling, for the equal equals, we are calling the three-way comparison and saying we want the equality check. But since we've just implemented the other operators, we can say something like 11 is less than 17. And this is also true, because we didn't crash. But if we say something like 11 is greater than 17, it also likes that for some reason. Let me print the result. Oh. Why aren't you doing anything? You're supposed to print something, but you're not printing anything. What? Ah, you're stuck in some sort of infinite loop. Okay, let me see what's going on. So what we're doing here is we're generating greater than, so we're here. So let's call a built-in debug break. And now the debugger breaks at this point. So let me look at the vstick pointer. We have 17 on top. Is that what we want? 17 on top. And then we are having 11. So the stack is correct. Okay, apparently it doesn't want to step over this one. Okay. Let me do something different. Print the stack at this point. So just so we can see what's going on. We've got -1 onto the stack, which is correct. Do we ever reach this point? We don't. So there's a bug in the CC instruction, which let me just see what the CC instruction is doing. Love SSC, love VM execute CC. I've never tested that in love code and it shows. So we forgot to increment the instruction pointer. Okay, so now this works. So now we can properly assert that 11 is bigger than 17, and we get an assertion failure because 11 is not bigger than 17. Okay, this was more difficult than I expected. It's helpful if you implement your virtual machine correctly. But anyways, let's commit that. We've added the comparison operators. In a similar spirit, we can implement all the other binary operators now. So for that, let me see if I can keep track. So we've got addition, subtraction, multiplication, division, modulo. Or it's remainder due to some sign stuff. So remainder. Then we've got the bitwise operators, bit and, bit or, bit XOR, shift left, shift right. Those are all binary operators that we are implementing for now. Assignment is another binary operators, but we don't have any L values at the moment, so it doesn't make sense to assign stuff. And then we've got the logical AND and logical OR, as well as the comma operator, but they have issues with sequencing because they only evaluate the results in. We'll tackle them later. So same thing as we did for the comparison operators. We just need to add them here. Maybe my language server still doesn't like me. So let's do it manually. Minus times. How did you know? And I forgot the scope. Of course, double percent. Okay. Let's add them to the parser as well. So let's look at the standard. So we were here, we're moving our way down. So now we've got shift. So shift. This is also left associative. Yeah, everything is left associative from this point. Shift infix shift left and shift right, shift left, shift right. And the operand is additive, no, additive, which is plus and minus, plus and minus, and the operand is multiplicative, which is times div and remainder, and the operand at this point is cast expression, which we don't have, so this one is the atom. I don't know what this issue here is. The operand here is shift, and then we've got and XOR OR. XOR and OR, and this is also the one that we are starting with. So let me just double check. We've got OR and OR, XOR, AND. Okay. Now there is an issue here due to the way, because Lexi doesn't have a tokenizer. It simply tokenizes stuff on the fly as necessary. There is an issue with the maximal munch rule. So at this point, it tries to see, like when, for example, when it tries to pass something like one, like a left shift, it will reach into the relational, try to pass a relational operator. It will see that we have a less than and successfully consume that less than, which is then an error because we wanted to do a shift. Traditionally, you'd have a separate tokenizer step, and then you didn't have that issue because token it will try to find the longest token that would match, and this isn't the case here. So this isn't what we do. So we have to manually tell it that we that to make it aware that there is a left shift operator at this point. This is done by using not followed by. So we only want a less than if it's not followed by another less than. Let's just make this one more verbose by saying if it's not followed by another punctuation. If it is followed by another punctuation, it is a different operator. And similarly, we need that here. By Lexi lit ASCII punctuation, and that way it will not see just attempt to match only one less than if it's not part of the correct operator. This doesn't work because now we forbidden something like 1 plus 3, which is of course equal to 1, 3. So I have to say, okay, not followed by another left one. Okay. This is something this is one disadvantage of doing things without the tokenizer. And this isn't something that I really like. But the upside is, if you don't have a tokenizer, in many cases, you know exactly which sort of token comes next. For example, when we do pass here function declaration, we know that we have like an open race as part of the block statement. And then it doesn't make sense to run the entire tokenizer to figure out, oh, what token could this be at this point, because we know exactly which one it is. So it's more efficient that way to do it on demand. But the downside is that we have to teach it things like maximum untrue manually in places. There's also like a potential issue once we deal with the... So this is only an issue here, because less than comes first before shift. If it were the other way around, we will first try to match shift, and then less than, and then this won't be an issue. But if it's this way, then you have to watch out for that. It's a bit annoying, but again, as a trade-off. Okay, so now we pass them, and the same deal, we need to add them to code chain. So, and this is the exact same principle. So we've pushed the values onto the stack already, so we just need to consume them. So for add, we're calling a built-in b love lib int signed addition, and there can be integer overflow. The C standard says integer overflow is undefined, so we could do whatever we want on overflow. For example, we could say overflow wrapped, and then we have the signed addition many people actually want, where overflow wrapped. But I'm not going to do that. Instead, I'm going to say we panic on overflow. I don't like overflow. It's an error if that happens, so you should panic. So let me copy paste this code a bunch of times. So we want subtraction. And note that loaf operates on 64-bit values. So integers in loaf are 64-bit. And we are directly using them for ints. So ints in our implementation are also 64-bit. And that's something we're allowed to do, and this is something that actually makes a lot of sense. So our integer are 64-bit. Division. Fun fact, division can actually overflow for signed integers, due to the way that because 0 is considered like a positive value, their int min is there's an asymmetry. So minus int min is not int max. In fact, minus int min is an integer overflow. So if we divide something by -1, we get an integer overflow. And this is the remainder. For similar reason, modulo can also overflow. Because if we do int min modulo -1, the compiler is allowed to lower that into a single instruction that does both division and modulo at the same time, and the division part will overflow. So modulo will also overflow. This means that to actually implement like a modulo that doesn't overflow, you have to check for the case when you're having admin and manually do that, which is annoying. But anyways, so those are the arithmetic ones, and then we've got the bits ones. So need to include a separate library for those. Bits and bits or XOR shift left. We want this shift left. And for shift right, so shift operators are interesting in C, because there are a bunch of undefined behaviors in their shift operations. For example, x -1 is undefined, because you're shifting, right? This should be x /-1. There's also undefined behavior if you do. Let's actually read the standard. So expressions, bitwise shift operators. If E1 has an unsigned type, then we don't have overflow. If E1 has a signed type and non-negative value, and the result is presentable, that is the value. Otherwise, the behavior is undefined. Because so a shift left isn't defined as a multiplication, which can overflow, which can lead to undefined behavior. And for right shift, we get an implementation defined value. If we do a division, if we essentially having like a negative value, if we shift this one over. So a negative value is like a bunch of ones, right? And so when we shift this one over, we get like fewer ones. But the question is, do we fill those up with zeros? Because then the resulting value would be positive. Or do we fill those up with ones? Then we would keep negative. And this is implementation defined. But all implementations, I think almost all of them, fill them with ones, so the value stays negative, which is also what loop is doing. So implementation defined behavior. We're doing what's called an arithmetic redshift. This is using the signed shift. There would also be an unsigned shift, and this would then fill it with zeros. And here we're having undefined behavior, but on overflow, but we're defining that behavior. So overflow wraps around and is not undefined. Because like we want to shift by left, it makes sense to view those as bits operation and not as multiplication, and it's perfectly defined if we do it in terms of bits. Okay, so those were the operators. Oh, right, this is add and sub. This is what the compiler has been complaining about. So let's test those out. So we want to assert that 1 plus 2 is equal to 3. And 1 plus 2 is equal to 3 because we haven't fit. Let's in fact print this. So, 1 plus 2 is 3. Excellent. Let's see whether we can do. So this should be 7. And it is 7. So let's shift everything over by 2. So 7 shifted over by 2 is the same as multiplying by 4. So this should be 28. And it is 28. Excellent. So we implemented binary expressions correctly. Well, those ones. Okay. So the first thing that's missing right now is we made one to parenthesized things, right? I find it curious. And this does work because we haven't dealt legacy with parents. And the way this is specified in the standard, let's look at the grammar again. So an expression, we've been following those ones. Then we've got cast expressions, unary expressions, we're skipping a bunch of those, postfix expressions, and then finally we have what's called a primary expression. And this is like the equivalent of the, let me open the parser, equivalent of this atomic rule. So what is the core operand of an expression? It's called a primary expression. It's a bit weirdly formatted here, but this is an identifier, a constant, a string literal, an arbitrary expression in parentheses, or generic selection. So currently it's only a constant. So let's add a parenthesized thing. So parenthesized, and then we want to recurse and pass another expression. And we have to do it in this order because we have to use LC. Okay. Right. So now we need to add another overload, because an atom previously could only produce an integer constant expression, so this is what we're returning. But now it can also return an arbitrary expression, so let me just change this parameter so it returns an arbitrary expression. And now it works. This should now be 36. Let me move the shift. Nine. 1 plus 2, 3, 9. Right. And this was very easy because parentheses only define the precedence, which means that they don't only affect parsing, but doesn't need to show up in the AST. So let me compare the two things. 1 plus 2 times 3. So here in the first call, we're having a binary expression that is a multiplication, and its child is an addition, and then the number 3. And here in the second case, we are having an addition, and its child is the number 1 with multiplication. So there's only changes like which way the tree is organized. So we don't need to do anything else to support parts. So. Something we can do while we're at it is we don't need casts because we only have one type at the moment, so no need to add casts. The other, like we don't need size of, line of, increment, decrement because we don't have anything to increment or decrement, but we can implement the unary operators. So let's add, well, except for address of and dereference, but we can implement those for us. So let's add them. First, we need another node for our AST, which is a unary expression. Here we can essentially copy, copy this one. Unary expression. It's a unary expression. We are having plus, minus, not, yeah, not until, so let's call this bit node, logical node. So this is still this is that. We take a type. We only having a single child. So we insert a single child into the tree after the type, which means that we are only having a single child, not a second one. Okay. That's the node, which means we need to print a new node. Need to print a new node here. Let me actually rename those. So because I've been naming everything else after the role and not after the symbol. So let's not call this one minus, let's call this negate, and let's call this, I mean, this is like the integer promotion operator. Let's just call this one, yeah, let's just call this one plus. And didn't like the rename. It did like the rename, okay. So now we print those, and let's also add them to the parser. So we've got a unary expression at this point. This is defined a bit, no, right, because it's a post prefix operator. So this is a prefix op. We don't have to worry about associativity for prefix operators. So op, same deal. Unary expression plus gate bit not. Right, this is the logic. And the operand is the atom. And here the operand is now a unary. Why are you complaining? Must be a type. Oh, I'm missing an O. Right, and then we need another overload here. So in this case, we are getting a unary expression operator with a single child. Again, we know the type statically because we're only having one type, and then we create a unary expression. Okay, this compiles. Let's add them to CodeGen. So same deal, just with a single value instead. And then we just need to do the appropriate operation. When we do plus, we do nothing. Because plus doesn't do anything. Negation. There is no single negation operator in love. So what we need to do is we push a signed integer onto the stack with the value -1. And then we are calling built-in for multiplication. Signed multiplication, and we want panic on overflow. Because again, int min, we can't multiply that. Here we have a built-in. Love lib bits not. And here we want to essentially, if there is a single bit set, we want a 1, otherwise we want a 0, right? Because it converts it to a Boolean. So we are calling the built-in bits any set. Any bit set produce 1, otherwise produce 0. Okay, let's test it out. -1. Yeah, let's just print -1. -1 is in fact -1, so that's good. What about tilde? It's -2, because we've negated everything but the last bit. This is correct. And when we do that, we get 1 because the bit has been set. Okay, let's just, because we haven't tested it, try out integer overflow. So we get int min, which is 0x. What's the way to get int min? That should be int min. Let's subtract 1. And we have an integer overflow. Excellent. And also, this is what I meant with the minus operator. right? We can't negate int min. So this is also an integer also. Excellent. I prepared a test case at this point, which should succeed, but it doesn't. So arithmetic.c 005a would be great. If I knew which one that was. Need to add debug info soon. 005a 005a is the assert for the not. Not 0 is equal to 1. This one, really? Not 1. Not 0 is should be 1. Right. So what's going on here? I did test this function, so this said if this is not 0, then we produce 1. And this is in fact 0. So this appears to be doing nothing. We're having a Unary expression for the correct type. So this isn't the issue. Let's print the values we have on the stack. So we're having on the value stack the value 0, and then we're also having the value 0. So this didn't do anything. Interesting. Is demo? Oh. Have I seriously messed that one up? This is false, so this is 0. Oh, of course. Yeah. If any bit is set, produce 0, otherwise produce 1. We want to flip it around. I've just what I did was I converted an integer value to bool, but we wanted the opposite. We want to convert it to bool, and yeah. So that is great now. Arithmetic succeed. We're still having a bug in comparison. 34. Version failed 34, which is converting 3 to 5 less than. Oh, of course. The test is simply broken. Okay. So now those bugs. Okay, we're now having unary operators, which tackles most of the expressions. So what's left are the logical ones. We'll take care of those soon, but let's do something more interesting. Conditional expressions. So we want to see whether something is true and then evaluate to something or evaluate to something else. So same deal, we need a new kind of node, conditional expression. then we copy the U. This is a conditional expression. We're only having one, so we don't need this. Conditional expression has 3 children. We are having the condition, and then we're having the if true expression, and then the if false expression. So condition, if true, false. Which means that we've got the condition, then we've got the if true, which is the child after the condition, and then we're having the false, which is the child after the if true node. This means new nodes. I really wish for reflection so we can automate this entire boilerplate away. Conditional expression, conditional expression. Conditional expression, we don't need to do any special printing because the default print prints all the children, which is all the expression has on data, so we don't need to print it. So that's good. Parsing. Parsing is a bit interesting because a conditional expression has like, it's not a binary operator, right? It has 3 operands. We're having the condition, then we're having something, and then we're having something else. And this can be fast as a binary operator in a neat way. Because as you can see for the precedence, on the left-hand side, we're having something of lower precedence. And here on the very left, we're having the same thing. So it's a weight associative operator. But here in the middle, we're having an arbitrary expression. So in a way, the middle thing is parenthesized automatically because this can have any precedence. So what we can do as a trick, we can consider the entire middle thing as an operator. So the operator of the conditional expression consists of the question mark, an arbitrary expression, and then a colon. And then this is just a right associative binary expression. So let's pass it with that. Conditional. It's a right associative binary operator where the operator, we don't need DSL op, is it's a question mark followed by an arbitrary expression followed by a colon. And the operand is no expression. Conditional. So here expression if true. Again, we're hard coding the type. Conditional expression condition if true false. Function to call of type right on. This is the lambda. The R method is sometimes here. We are clearly got more arguments. Want to figure out what exactly is the. Oh, right. I believe the issue here is that DSL op wraps, produces a value, but we don't want a value. I believe I can use void. Yeah. Okay. Let's see whether this passes. Uh, 142. And that passes. So we've got a conditional expression condition is 1, left is 11, right is 42. And then we're not handling it in CodeGen, so we're getting an error here. So let's handle it in CodeGen. So a new kind of expression. Now, CodeGen for this is a bit tricky, because we can't just wait until all the children has been visited, because at this point, both arms have been evaluated, and we only want to evaluate one. So we need to manually visit the children at the correct type. This can be done by providing here a child visitor. So, additional expression. So what we need to do is, first step, evaluate the condition and push it onto the stack. So this can be done by visiting the condition. That's straightforward. So we are recursively visiting the condition, which will push it onto the stack. This will then recurse and call the appropriate overload. Now we want to make a decision. If the condition is 1, we want to evaluate the first child, otherwise we want to evaluate the second child. And this requires a branch in the assembly. And the way assembly works in Lope is we've got these basic blocks, which are a logical sequence of statements. And to do a branch, we need new basic blocks. So we need 2 new basic, rather 3. So the first one is the block if true. So this is the block where we jump to when the condition has been true. Fill those in later. Then we need a block that we jump to when the condition is false. And finally, we need a block that we jump to in the end of both branches. So we continue on. Each blocks may need can accept values. So in this case, we want to preserve all the values that are currently on the stack. So for example, the code can look like this: 1 plus condition RB. Then when we evaluate the conditional expression, 1 has already been pushed onto the stack, and we need to keep it there so we can access it. So the plus, when the plus evaluates at the end, we keep it there. So we need to pass all the values that are currently onto the stack to the blocks. So cur stack size build get the size of the stack. So when we call if true, we keep that many values onto the stack. And then each if true and if false both evaluate to one additional value, which will then be passed to the end. So when we go to the end, we're having one further value. So let's evaluate the condition in this one. Okay, now if the condition is true, we want to go to block if true, otherwise we want to go to block if false. So we do a two-way branch of the value that is on top of the stack, which is 0, 1. If the branch is true, we go to block if true, otherwise we go to block if false. So we have the if true case. So then we start building the block for if true. So we stop building this block because this branch 2 is also a terminating extraction, so our current block is now finished. So we start building this block, and at this point we evaluate the if true case. And this doesn't and like this will then push its value onto the stack, and then we just jump directly to the end block. Similar for the false case. We evaluate the false expression and go to the end of the block. And then we just continue, but in the new block. bit block. So anything else that happens, any subsequent evaluation happens in the common block after the correct branch. So you're having a bunch of implicit conversions. Let's just handle those right now and update the API later. Let's see what happens. Our condition is 1, so we're pushing 1. Right, so we're pushing 1. Then we're doing a two-way branch. If the branch is false, we jump to 5. If the condition is true, we have a fall through and go here. So if the condition is true, we don't jump. Instead, we push B, which is 11, and then jump to 7. And if the condition is false, we have jumped here, which pushes 42, and then we jump to 7 as well. At this point, we print, pop the value, and return. So when you print it, this prints 11. And if we turn this into 0, this prints 42. Let me see whether the addition example also adds. So this should print 12. And it does print 12. So this is where the block arguments are important, because we've already pushed something into the stack, so it needs to put those. The basic blocks, unfortunately, they have been removed by the point we render the bytecode. They're purely an implementation, an artifact of the way the API is specified, so we can't really see them. But like this is the first basic block. Then we've got the if true block here. This is the false block, and then this is the end block that we pushed afterwards. And now all the tests are prepared for us. Okay. To end the stream, let's just tackle the remaining general expressions we can handle. So the top level one, the comma, and then the logical and logical or. Those are a bit tricky due to the way conditional evaluation, but we'll tackle those in a similar way to the condition. They are binary expressions, but I will not treat them as binary expressions due to the evaluation concerns. So let's add them, call them ordered binary expression. Ordered binary expression. Sequenced. Yeah, just call them sequenced. Sequenced, and we've got 3. Got the logical or, logical and comma. Everything else stays the same. Sequenced. So this is that one. And comma. Add the parser. We pass them in the same way. So comma is the top level one. This is operator that is right associative. Apparently, and fix up right. Yeah, that makes sense. DSL up, DSL seek. sequence binary expression, comma, let's see it, comma. The operand is then directly a conditional expression. And the conditional expression has as a child or and then and. Right. Logical or, those are left associative, I'm assuming. And they are left associative. Sequence binary expression. And this is what I discussed earlier. Because we are first attempting to match 2 pipe symbols, we don't need to worry about maximum munch. Because if this one doesn't work, we only later try the single pipe. And binary OR. And then copy this one for sequenced binary expression, and then we return a sequenced binary expression. And again, we're only having ints, so that's our only type. That compiles. Now Gotchin. Because we only want to evaluate them at sometimes, we're also using the child visitor here. Sequence. So comma is the easy one. Comma is specified as evaluate the left operand. And in case you're wondering, comma operator is when you do I equals 0, 0, j equals 0, to a plus plus j plus plus. That comma here is the comma operator. It's used there, and when you want to fold over a parameter pack in C++ code. That's the only reason it exists. But it evaluates the left operand. Then it discards any value it produces. So we want to pop the value on top of the stack. And finally, it evaluates the right operand, and that's the value that's left on the stack. And OR have short-circuiting behavior, so if the result is already known, then it doesn't evaluate the left-hand side. So we evaluate the left-hand side. If this one is already 0, then it doesn't matter what the right-hand side is doing. Right? If it's 0, then it short-circuits, and we don't evaluate the right-hand side. So this means that we again need to do a condition, so we need blocks. We need a block if let's call this eval right and add. And if we evaluate the right-hand side, then we are keeping the same thing on the stack. And if we go on the end, then we've pushed the result. So we evaluate the left-hand side. If this one has been true, then we also need to evaluate the right-hand side. Otherwise, we don't need to evaluate the right-hand side. We know the result already. So we need to push the result. We already know the result already, which is 0. So this means that we need another block, short circuit. Then we short circuit. Then we start building the block for eval right. Block B. At this point, we evaluate the right-hand side. And then this produces a value, and this is the value of the final expression. Because we only reach this point if the first one has been true. So we just jump to the end. If we short circuit, then we know the result is false, because that's the result. B log and at this point, if left has been false, so that's the result. And then finally we start building the end. Build block. Similar, we just continue. Now I'm just going to be lazy and copy that for OR. But adjust the logic. So if the left-hand side is true, then we can short circuit, because the right-hand side doesn't matter. Otherwise, we need to evaluate. We only reach this if left has been false. Left has been true, so that's our result. And let me just reorder them. So, okay, I believe this logic is correct. Let's test it out. I always forget where the file is at. One and 0. Of course, since we don't have anything that has side effects, we can't really test the conditional evaluation at runtime, which is why I haven't written a test for it. So where do we fail? We are not parsing you. So the operand is a logical OR. So 1 and 0 is 0. We can't test the evaluation because we don't have side effects in our expressions yet. So, but we can expect it. So we push 1. If that has been false, we jump to 5, which pushes 0 because it has been false and continues. Otherwise, we fall through and push 0 because that's our right operand. Right, that appears to be the correct logic. Yeah, if you post, yeah, we can't really test this one reliably, but it appears to work. What do you generate for OR? We post 0. If it's false, we jump to 3, which evaluates the right-hand side. Otherwise, we immediately jump to the end. Yeah, this is the correct code. Let's just also test comma. Also pass comma. Yeah, comma simply evaluates the left-hand side, pops it, evaluates the right-hand side, prints it out. Okay. Okay, that has been about an hour, which is the target for stream. I've teased in the title that we will do proper declaration handling. I will move that to Thursday. So on Thursday, I will be streaming again. And there I will finally start doing something so we can have anything other than constant. I will add local variables. So we can then add local variables, maybe manage to access them and modify them. So add assignment and identify access. Thank you all for stopping by. Hope you enjoyed the stream, and until Thursday.